Thank the organizers for having this wonderful conference, and it's my great pleasure to speak here. So today we have here a lot about the neural encoding of speech. And when we listen to speech signal, of course, we first hear speech as a sound. When we just look at the acoustic waveform of a speech signal, the most salient feature that we see is that the energy of speech will fluctuate up and down, which is reflected by the temporal envelope of speech. And of course, speech is not just a sound signal, it has its own linguistic content. So if we look at the linguistic structure of speech, and here I'm showing the syntactic structure of speech, which describes the syntactic relationship between words. And then we see some additional very complex hierarchical structure embedded in speech. So the question that we are trying to address here is that when we listen to speech, there will be ongoing neural activity encoding this very dynamic speech signal that we hear. And our question is, we know that speech has certain acoustic features and certain linguistic features, and we want to know how those kind of features are encoded in ongoing neural activity. So in the following, I will first give a brief introduction about the temporal structure of speech, and then talk about the neural encoding of hierarchical temporal structure in speech, and finally about how attention may modulate this kind of neural representations. So as we already hear from this conference many times, so this kind of acoustic temporal envelope of speech is related to the boundaries between syllables, because each syllable has a vowel which has high sound intensity, and that the boundaries is usually consonants or some short pauses which has low acoustic intensity. And this kind of acoustic fluctuation in speech is, of course, not periodic, but it's sort of quasi-periodic. And we actually did an analysis of the power spectrum of the speech envelope based on large corpora for many, many different languages. And what we saw is that actually, no matter what the language is, if we just treat speech as a sound and look at the acoustic envelope, the spectral property of the acoustic envelope, what we saw is that there's always a resonance peak between 4 and 8 hertz, which is related to the syllabic rate of speech. And actually, one thing that I want to mention here is that although we see this kind of resonance peak, and this peak is not language dependent, but this peak is actually a very broad peak. And also, this kind of peak is observed only for the power intensity in a logarithmic frequency scale. And for this kind of power intensity plots, 1/f noise will be a flat line. So this kind of resonance near 4 and 8, between 4 and 8 hertz is actually a contrast between the speech modulation spectrum and the modulation spectrum of just 1/f noise. And so here we see that there's some uniform feature of the acoustic rhythm of speech. But how about other sounds? Are they all the same? And the answer is no. So we also look at the modulation spectrum for classical Western music played by different musical instruments. And we saw is that no matter what the musical instrument is, whether violin, piano, or cello, the acoustic modulation spectrum of the music recording is also very consistent. And they all have a very similar peak, but the peak this time is below 2 hertz rather than between 4 and 8 hertz. So by comparing the modulation spectrum for speech and modulation spectrum for music recording played by single instrument, and also, for example, ensemble music like jazz, rock, and symphony, we can see that for music, usually there's way more power in the lower end of the spectrum, but for speech, it's usually some kind of resonance between 4 and 8 hertz, even though it's not a very sharp resonance. And based on, a lot of groups, and including ourselves, we have seen that when we listen to speech, there's the brain can synchronize to this kind of acoustic rhythm. For example, here, the red line illustrates the acoustic waveform of a speech signal, and the green line is what we decoded from the ongoing MEG response using a machine learning method. And we can see that the decoded speech envelope is very much similar to the actual speech envelope that the subjects hear. And also, so here we see that the neural response can track acoustic envelopes, and also first recording obtained from ferrets, we see that actually it's not just that the neural response is synchronized to the acoustic features of speech. It's also that if you look at the intertrial variance or the induced power of speech, of the neural response, we can see that in the for the low frequency band like alpha, theta, the intertrial variance actually decreases after the onset of a sentence. And of course, for frequency bands like high gamma, that the power actually increases because high gamma is more related to neuronal firing. So based on this, I mean, it's sort of phenomenologically is more or less like a phase resetting, but of course, as we already discussed in the morning, I mean, whether it's phase resetting or not, it's more or less like a philosophical question because we don't really know whether the oscillation before the sentence and after the sentence, whether they're really the same. Here, all what we see is that when the sentence starts, there will be evoked response tracking the sentence rhythm, and at the same time, the intertrial variance will be reduced. So speech irrelevant activity will be surprised. Okay, so far I have only been talking about neural entrainment to the speech envelope. But of course, we know that if we want to understand speech, we cannot just encode the speech envelope. We have to further, for example, group the different syllables into words. And this is actually a very challenging task because just in this example, vacation is a single word. But if you look at the 3 syllables in vacation, they're actually quite separated in time. And in contrast, actually the first 2 syllables, they went. Acoustically, they are really close together, but they are actually 2 different words. So based on just acoustics, it's actually very hard to find the boundaries between words, and we have to use our knowledge, lexical knowledge, to guide our brain to find the boundaries between words. And it's a similar case for when the brain looks for syntactic, the boundaries between syntactic units. The boundaries between syntactic units are not really clearly defined acoustically. In order to find the boundaries between syntactic phrases, we really have to use our syntactic knowledge. And so based on this, I mean, we can already see that in order to understand speech, we have to build new representations on different levels. We have to first represent the acoustic features of speech, and then decode the phonetic content of different phonemes, and then group the phonemes and syllables into words, and further group the words into syntactic units. So in order to understand speech, we have to build a hierarchy of neural representations of different linguistic units. And so it's still not clear, I mean, how the brain handle this hierarchy of neural representations. And our hypothesis is that for each of the linguistic level that's represented in the brain, there will be neural activity synchronized to the rhythm of that linguistic unit. Although I'm saying that it's synchronized to the rhythm of that linguistic unit, what I really mean is that it's synchronized to the time course of that linguistic unit, whether that linguistic unit is periodic or not. So, I mean, the underlying hypothesis here is really that, for example, if we consider the neural representation of a noun phrase, so when we are in a noun phrase, we want to integrate all the words within the noun phrase. So it will be very helpful to keep a consistent neural representation of this noun phrase until the boundary. At the boundary, this kind of consistent representation has to be recycled because very soon a new phrase will come. So the brain has to recycle the neural representation of the previous phrase in order to encode the new incoming phrase. So just by this kind of thinking, we think that I mean, there will be neural activity synchronized to the time course of a phrase. So the neural representation will start from the beginning of the phrase. It will either maintain a sustained activity or increase over time. And at the boundary, this kind of neural activity will recite. So this is all what I mean about this kind of hierarchical tracking of different linguistic levels. We don't really emphasize that there's a periodic nature. It's just that, I mean, there will be neural tracking of different linguistic structures on different time scales. And because the linguistic structures are on different time scales, so the neural activity synchronized to those structures will have different spectral properties. And so in order to test this kind of hypothesis, we designed the experiment like this. So we first synthesize a bunch of syllables using computers, and all the syllables are synthesized independently. So, for example, in English, all the syllables are actually monosyllabic words like dry or rubs or plants. And because all the syllables are independently synthesized, so there's no acoustic dependence between syllables, so there's no co-articulation. But when we concatenate the syllables into a speech stream, we ordered them so that neighboring syllables or monosyllabic words always combine into a phrase, and neighboring phrases are always combining into a sentence. So in this kind of syllable sequence, we are embedding 3 different linguistic levels. One is at the syllable or word level, and another at the phrase level, and a third one at the sentential level. And when we made the material, we had a trick so that we adjusted the duration of all the syllables to be the same. In this case, it's 250 milliseconds. And we didn't add any acoustic gap between syllables. So the syllables are presented at an isochronous rate of 4 Hz. And because each phrase has 2 syllables, so the duration of a phrase is twice the duration of a syllable. So the phrasal rate is half of the syllabic rate, which is 2 Hz. And similarly, so because each sentence has 2 phrases, so the sentential rate is half of the phrasal rate at 1 Hz. So the reason that we made this stimulus very regular and periodic is there are 2 reasons. The first reason is just to simplify the analysis, because if the stimulus is rhythmic, we can just look at discrete peaks in the neural response spectrum. And another reason is that because here we are playing sentences of the same structure, so they can have an expectation about the sentential structure. Because when people are processing natural languages, especially for complex sentences, they may have to reanalyze at some point for some garden path effect. So, but in this case, they all know the structure, so they can sort of, even for the first pass analysis, it will be correct. Okay, so this is, so for this kind of material, we had 2 versions. One's in Mandarin Chinese, and another is in American English. So this is the neural response spectrum for the Chinese material played to native Chinese speakers. We can see that there are 3 clear peaks in the neural response. One is at the syllabic rate, reflecting possibly the neural entrainment to the speech envelope. And there are additional 2 peaks, one at the phrasal rate and one at the sentential rate. So indeed, when we listen to this kind of materials, our brain is not just resonating at the rate of the acoustic input, it's also resonating at the rate of some abstract linguistic structure constructed by internal knowledge. But in order to make sure that these 2 peaks are really, the product of internal syntactic operation, we had a control experiment in which we present the same material, but this time to native English speakers who don't understand any Chinese. And this is the response to from the English speakers. And clearly we can see that they can still entrain to the syllabic rhythm, but there's no response at all at the phrasal rate or the sentential rate. And here I will play an example of the material. Oh, so even for the English listeners, we gave them a task. So we try to force them to group the syllables in groups of 4. So we ask them, when they're listening to the syllable, they should count 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And at the end of the trial, they have to report whether the last one is 2 or 3. And for the Chinese speakers, it was a semantic task. They're detecting some abnormal sentence. Okay, so especially if you don't speak Chinese, probably you can appreciate that it's a very regular syllable sequence, and probably you don't really hear acoustic groups of 4. Okay, so in the spectrum that I just showed, so these are just the spectrum of MEG responses, and these spectrum are average over all the MEG sensors. So it doesn't tell us where the neural response is from. It only tells us the spectral property of the neural response. So in order to figure out, where in the brain such the neural tracking of phrases and sentences is generated from, we also did the same experiment using ECOG. So this is epileptic patients undergoing surgery. And we had 5 different patients. 3 are implanted in the left hemisphere and 2 implanted in the right hemisphere. So the 5 patients are all native English speakers, and the materials were made in English. What we saw is that in the ECOG electrodes, we can find the electrodes that only show a response at the sentential rate, but not at the phrasal rate. And we can also find other electrodes that only respond to the phrasal rate, but not the sentential rate. So, and this figure shows where the electrodes are on the brain. And I mean, the empty circles means right hemisphere, filled circles means left hemisphere. We can see that although we can find electrodes only responding to sentence or electrodes only responding to phrase, they're not, I mean, those electrodes are really sort of mingled in their spatial distribution. Sometimes for a single patient, we can see that maybe one electrode is responding to phrase and a neighboring electrode is only responding to sentence. But of course, there are also electrodes responding to both. And additionally, we can also find electrodes that respond to either the sentence or the phrase, but not responding to the syllabic rate, which is also interesting because the syllabic rate is really a very salient feature in the acoustic signal. But those electrodes are not really responding to that rhythm, but instead encoding the rhythm of some more abstract linguistic structures. And later, so this is based on ECOG, and later on, we saw that based on the MEG response, we can also separate the neural encoding of the 1 and 2 Hz and the neural encoding of the 4 Hz. We can do a component analysis on the MEG data, which is more or less like ICA or PCA, and we can see that the 1 Hz and 2 Hz are decomposed into the first 2 components, but the 4 Hz are in the later components. So based on either ECOG or MEG, we can say that the neural encoding of the more abstract linguistic structures is not generated from the same neural network responding to the basic acoustic rhythm. Okay, and finally, so as I mentioned before, so we designed our stimulus in a very periodic way, but we don't really think that this kind of periodicity is really necessary to see the neural entrainment to larger structures. So in our original study, actually, we also had a condition in which we had sentences of different durations. So some sentence has 4 syllables, some have 5, some have 6, or 7, or 8. And when we present these sentences, we mix them all. So for example, a sentence of 4 syllables may be followed by a sentence of 6 syllables. And this kind of order is completely randomized. And what we saw is that after the sentence onset, there will be a neural response, and this kind of response will slowly return to sort of the baseline at the end of a sentence, no matter how many syllables the sentence has. So this kind of slow tracking of the sentential structure exists even when the sentence has irregular duration and actually irregular syntactic structure. And furthermore, we also had an experiment in which we had short sentences that's always a noun phrase followed by a verb phrase. And the noun phrase is sometimes 3 syllables, and sometimes it has 4 syllables. And we also see that there's also a response tracking the boundary of the noun phrase, even though, I mean, the duration of the noun phrase is not really predictable. Okay, so to summarize this part, we see that indeed, when we listen to speech, there's not just neural activity entrained to the basic acoustic rhythm of speech, there is also neural activity entrained to higher level linguistic structures. And the neural tracking of different linguistic levels occurs in spatially separable neural network distributed across STG and IFG. So largely speaking, I mean, this kind of hierarchical tracking model is roughly correct. And in the following, I will try to figure out whether attention is needed to build this hierarchy of neural representations. Okay, so in the next experiment, so we had a very simple stimulus in which there is a sequence of bisyllable words like teacup, highway, textbook, and skyline. Of course, this is still made in Chinese, but showing English for illustrative purposes. And furthermore, we had this kind of bisyllabic word sequence in the middle of some random syllables. So at the beginning of the trial, the subject will not realize that they will hear a sequence of bisyllabic words. And like in the previous study, we adjusted the duration of all the syllables to be the same so that it's just a isochronous syllable sequence presented at a rate of 4 Hz. And in the experiment, we had different tasks. So in the first task, they will listen to this kind of isochronous syllable sequence in 1 year, but in the other year, they will hear a natural story. And this story is time compressed by a factor of 2, and all the long gaps in the speech signal are removed. So that, this speech signal is still perfectly intelligible, but it's very challenging to understand this kind of signal. So it will attract a lot of attention. So in this experiment, the subject will either listen to the syllable sequence or listen to the time-compressed story. And in another experiment, so they will either listen to the syllable sequence or they will just watch a movie. And this is the neural response spectrum in the first experiment when they did dichotic listening, so syllable sequence in 1 year and time-compressed speech in the other year. So when they are attended means they are attending to the syllable sequence. So when they are attending to the syllable sequence, we can see that they have a response at the syllabic rate, and there's also a response at the word rate because each word has 2 syllables. So the word rate is 2 Hz, half of the syllabic rate. However, when they are not attending to the word list, when they are listening to the time-compressed speech, the syllable response is reduced in size, but still significantly above chance. But the word rate response is no longer significantly detectable. So indeed, we really need attention to group different syllables into words. Even if, words are really fixed items stored in long-term memory, but constructing them online without any prosodic cues still requires memory, still requires attention. Oh, and this figure is just showing that comparing the attended and unattended responses, the response at the word rate is dropped by more than 80%, but the response at the syllabic rate only drops by 40%. And we saw a very similar pattern when they are watching a movie. So even if, during the, so it's a silent movie with subtitles. So there's no competing auditory input, but still, when they are listening to speech, we see 2 peaks at the syllabic and word rate. When they are just watching the movie, which has only visual information but no auditory information. But even in that case, we didn't see a significant response at the word rate. And here I'm just showing, I forgot to mention, so this study was done in EEG. And here I'm showing the EEG response average over all the channels. And we can see that when the subject hears the random syllables, there's some very regular fluctuation in the EEG response, which has 4 peaks in a second, which means this is a 4 Hz oscillation tracking the syllables. But when the bisyllabic words appears, gradually this kind of 4 Hz oscillation sort of slows down into a slower oscillation, and the intervals between the major peaks in the response waveform is sort of lengthened by a factor of 2, so it's really tracking the word duration. So this response is the response when the subjects are listening to the word list. When they are listening to the, time-compressed story, we still see an entrainment at 4 Hz, but when the words start, we didn't really see a clear trend, tracking the word duration. So in this figure, I'm showing the temporal envelope of the neural response at the word rate, which is in orange, and also the temporal envelope of the syllabic rate response, which is in blue. So the upper 2 panels shows the response during dichotic listening. So attended means listening to the words. So after the word onsite, if you're attending to the words, the word rate entrainment will increase, and actually the syllabic rate response slightly decreases. But when they're not attending to the word list, there's no such change in the response power. And when they're watching a movie, again, we see that if they're attending to the words, the word rate response will increase, and the syllabic rate response will decrease. And when they're watching a movie and not attending to the words, actually, we also see a trend that the word rate response may go up. It's not extremely significant, but there is a sign of the response. So when there is no very challenging competing auditory input, maybe there will still be a weak neural response to the words. Okay, to summarize this part, we see that, when we listen to speech, there will be neural activity entrained to multiple linguistic levels, from syllables to words to phrases and sentences. But when we don't attend to speech, there's mostly, neural entrainment to syllables, but the neural entrainment to even words is diminished. And to summarize this graphically, when we attend to speech, we have this kind of neural entrainment on different time scales. And when we don't pay attention, we only see a weakened neural response at the syllabic rate, but we don't see a clear response corresponding to the higher level linguistic structures. Okay, finally, I want to thank all the people in my lab and all my collaborators, and thank you for your attention.
Thanks, Nai. Questions? Many questions? You can go here.
I have a very basic question. So all your analysis, you're using FFT to decompose the signal? Because you wrote a paper where you were saying that FFT was maybe not... So isn't it surprising that you see the peaks by using FFT decomposition, because it might not be sensitive to see entrainment?
Right. So, actually, what we want to say is that, it's really this kind of slow entrainment. I think what I mean by that paper is that if there's only short, lasting on-site response at the boundary of each phrase, for example, that kind of transient response at the on-site will not really be reflected by the neural response at the phrasal rate. It will be reflected by the harmonics at that multiples of that rate. But here, what we saw is really, there's a response at the phrasal rate, which means that there is this kind of slowly changing neural response, not just transient activity at the boundaries.
Yeah.
Thank you, Nai. It was, as usual, very good. I have one question, for you. So I'm wondering, I think you're really trying to push the limits here where we can track stimuli that we're not attending to, right? And I think that you're trying to really build a strong case that it seems that every hierarchical structure is lost when we don't attend. However, we can anyways, in a conversation, for instance, understand that our names is being called up, even if we are not. So I'm kind of like, maybe wondering where this is not a limitation of the technique, as opposed to, that we are not really integrating those units. And what would happen if you, instead of using, if you would use say like a mismatch paradigm, where you would use all the time, like, double words over words, and then suddenly, you would switch. Would you not anyway look, observe there a mismatch negativity, for instance?
Right, very good question. I think Ilana has data related to that, yeah. So actually for the cocktail party phenomenon, so that you can hear your names in the unattended year, I think that only occurs for about a third of the subjects. So not everybody can hear that. And also, I think in, for example, Cherry's study, they use speech signals that's presented at a relatively slow rate. So here we are presenting everything at an extremely fast rate. So for example, we time compress the speech signal. So in order to, also for normal speech, there are gaps. So you get some chance to, not listen to the attended speaker when there's a gap in that speech stream. But we sort of try to get rid of all those things in the competing stream, so that in order to understand this kind of time-compressed speech, you really have to focus, entirely focus on this speech stream. So that could be one possibility why we didn't really see a response to words in the unattended ear. But of course, for example, during movie watching, we see that, the word response is still there. It's just weak and not as significant as the response when the word lists are attended. But still, there is something here. So Of course, I mean, this is related to task difficulty. If the competing task is extremely hard and you have to pay 100% attention to the competing stream, maybe you won't have a response tracking higher level linguistic structures. And probably in those cases, you may not respond to your name in the unattended ear. But of course, I mean, if the competing task is easier, you will get a chance to switch your attention and check both ears. And I think, I mean, in those occasions, maybe you have a higher chance, I mean, seeing the neural response to higher order structures. And also, of course, as I mentioned, I mean, only about a third of the subject can hear their names in the unattended ears. So maybe there's some individual difference which we haven't really looked into yet.
Thank you very much for your very interesting talk and very interesting work, which is very nicely at the interface between entrainment and getting some idea of syntax and hierarchical structure, which language is all about also. What I'm wondering is, the point has been made before, that you have very regular time intervals for your syllables and words and phrases and sentences. Well, one comment perhaps is that beyond noun phrases and verb phrases, we have clauses, right, which also organize, which is a level of organization also. But if you look at the higher level, at the sentence level, I mean, in natural language, there's a huge variation in the duration of sentences, and even in the duration of clauses, if you would take it one level lower. But let's say if you have an average sentence of 10 words, it would last for 4, 5, 6, 7 seconds. So that would mean that if you would have to fit an oscillation through that, you get that oscillation
very
of
slow,
0.2 hertz. I'm not sure whether I've been seeing that in my EG, MEG recordings. So question is
very good question.
Yeah.
So I think there are two aspects related to this. So one aspect is that, I mean, of course, I mean, there's a lot of low frequency noise, 1 over F noise in the MEG and EEG recordings. So it's fairly difficult to see anything that's extremely slow. So maybe there will be something there, but it's just very hard to see. Even 1 hertz is fairly hard. And another thing is that, I mean, I think this kind of, entrainment model works better for shorter sentences. If the sentence is too long, of course, if the sentence is like a minute long, we will not able to process that because that's beyond our limit. For a normal sentence which is long, but we can process, probably we will also, in those cases, maybe, the phrases will be the sort of the master level. And if the sentence is too long, maybe it's really hard to maintain either a sustained response or some monotonic increase or decrease in your activity. So in those cases, maybe, the phrases will become the dominant component. Yeah.
Questions? Yeah. Come over here.
It's a question about the functional role of the higher order, entrainment. So in the very early stages, the signal recorded from the brain is very similar to the acoustic signal to the point that you can reconstruct it. Can you reconstruct something from the higher order entrainment, the syntactic structure perhaps, which is what is common across all these sentences? And relatedly, if you had played with two structures, both with forwards, do you think you could separate them in those frequencies?
Right. So in our previous work, we tried to decode sentence duration from our data, but of course, that's a very rough measure. That's only, about what's the duration of the sentence, not really about the detailed structures. I think Alexander has some nice data, trying different structures, and it would be nice to see if we can decode, the syntactic structure from low-frequency responses. In terms of the functional role, I think, I can only guess. One possibility is that, some kind of online integration. So this reflects the integration of information over time. And of course, it could be, for example, what Odette suggests. You sort of package things up at the boundary and send that to higher order cortices. I think, related to the functional role, we can still, we can just speculate. I have no real answer for that.
Other questions?
Okay, thank you. That was great to see all this stuff together. So I just wonder whether you could put back the slide where you had this EEG recording, which was, very regular during the, and then, kind of slowed down. So I just wonder what kind of interpretation you want us to get out of this, because do you really want to say that you're losing the theta,
No.
4 hertz rhythm in the middle?
You just, a new component is added in, so it's no longer like that. But of course, as we shown using the Timecourse, maybe there's a small decrease in the syllabic rate response, but of course, it's still, still there. Okay. If you filter the response, for example, just near 4 hertz, you will see that, there's just a small decrease. Yeah.
Okay. And so what was the proportionate amount of those bisyllabic chunks in your entire stream? So the reason why I'm asking that, if you went again back to the slide where you had the 2 hertz rate in addition to 4 hertz. So in order to get this, let's say you only had 10, it's a basically very boring question, but it's like, to the extent that my entire, 90% of my stream does not have the 2 hertz rate, how come I get this?
Oh, actually, so for that spectrum, we only analyzed the response during this portion. So yeah. Okay.
David? No, we're recording, so just wait a second.
Better think of a question. So the attention work sets up an interesting tension, unintentional pun, between that structure building is effortful and requires attention, which contrasts in an interesting way with other people's theories. And I'm thinking here, for instance, of a recent paper by Tecumseh-Fitch, that structure building is actually kind of the default of the brain. That is, it's not effortful at all. It's what we're naturally inclined to do all the time. And so I wonder what you think about that. You're suggesting that for this particular task, it requires more heavy lifting and attentional demands. But if we believe Tecumseh, we never have to do anything. It's like falling off a truck. Building structures is just what you do. It's like opening your eyes. So it's a very different kind of theoretical proposal.
I think, it depends on, how you do structure building. For example, in Odette's talk, we hear, chunks of digits. I think in those cases, if there are prosodic cues, probably, the grouping is automatic. But here, of course, even if for Chinese it's not hard to understand this at all, but still, there's no acoustic cue for the word boundaries. You really have to use your linguistic knowledge to find the boundary. So I think in this kind of more challenging case, you really need attention to figure things out.
I'm going to jump in here also, David, and just say that that's what I'm going to talk about in a few minutes. So I think we can have a deeper conversation after we give some more data on this.
Okay, perfect.
Yeah.
No, I think Lars, and then
just on what David said, I think I agree with him, because we see the exact same effect that you show for words using very simple stimuli like pure tones. So if the animal is ignoring them, entrainment completely goes away.
But what do you mean by words? Like
the effect you show on phrases and words, so that it might not reflect the building of these structures, but rather that the brain, because it's attending to them, is operating on them. Because you see the exact same effects with just very simple stimuli that don't need, segregation or anything like that.
Cool.
That's all.
Yeah, and as you mentioned in your talk, we can learn the statistics of the stimulus even when we are not paying attention. So there is definitely something running there, yeah. Okay.
So my question may be related, and it's rather just a terminological one, I think. So when I take your data seriously, so the first data that you showed about the hierarchy building, I always have a hard time understanding why you call this entrainment. Because
I call
entrainment
that phenomenologically, actually.
Yeah, because for me, entrainment has always been something that is driven by something external in the stimulus. It induces its rhythm into the brain. And in this case, there's nothing in the stimulus that could drive this frequency in the brain. So this is not entrainment, this is projection. The brain does something actively, and that's what you measure. It comes from the top down.
Yeah, I mean, I think David was just suggesting that this is entrainment to internal rhythms. But of course, I mean, as we also discussed in the morning, I mean, there's no clear definition for entrainment. I mean, we use it in a very loose way. I mean, we just mean there's something synchronized to the stimulus. I mean, in some sense, the structures are in the stimulus. It's just that, I mean, you have to use your linguistic knowledge to figure those things out. It's not in the acoustic signal, but it's in the input sentence. Right, I mean, if you talk about the acoustic properties, but you can also talk about the linguistic structure of the stimulus, right? Right, not in the physical stimulus. Right. Right, it's not in the physical stimulus. If you think, I mean, entrainment only occurs for physical stimulus, then this is not really called entrainment. It's sort of, I mean, using the term in a more loose way. I mean, basically we are trying to say, I mean, tracking or synchronization with the time course of some abstract unit. Okay.
So I'm happy about eating up arguments because the room is air conditioned, so it's really good. But maybe we can just carry it on later. And thank you for his great contribution.